So what we have in front of us is a acids and base topic test. So I will do the test myself. That will be the first try. And after doing the test myself, then you are gonna do the test. You can ask questions, I can help you out and so on. But I want to do the test first myself. So let's go ahead and take a look at it. If I'm doing something and then you don't understand where it is coming from, then you can ask me. Right. So question 1, we usually don't read these instructions. We just know what to do, but let's take a look and see what is happening. 4 options are provided as possible answers to the following questions. Each question has only one correct answer. Choose the answer and write only the letter A to D next to the question numbered 1.1 to 1.5 in the answer book, right? And then, for example, we have 6 with an answer being E, right? 1.1, consider the following chemical reaction. Let's take a look at that chemical reaction. Which one of the following correctly identifies the order of Florey-Bronsted acids and bases in the above reaction? Okay, so let's take a look at that. What do we have? We have HCO3 minus plus HC2O4 minus, giving us and getting H2CO3 plus C2O4 to the 2 minus. So let's go ahead and dissect this. Okay, so we start with HCO3 to the minus. So if this is an acid, in the product side we must get CO3 2 minus. It would have donated a proton and we would therefore refer to it as an acid. That is if and only if it is an acid, right? So let's go and check and see if that is actually the case. So let's take a look. We start with, let me just erase this. We start with HCO3 minus and then we end up with H2CO3. So it is not an acid because it is not donating a proton. It actually looks like it has accepted a proton. It was HCO3 minus, now it is H2CO3, right? So clearly it has accepted a proton. So if it is a proton acceptor, then this is our base because it has accepted a proton, and then this is going to be a conjugate acid, right? That is going to be a conjugate acid. And in doing that, I think we have for the most part answered our question, because if that is the base, then this is the acid where we are getting the proton from, and then this is going to be the conjugate base. So there we go. Our order, we have base, acid, acid, base. So let's go ahead and look at our question and see which option is that. So okay, B and C, well, B and D starts with a base followed by an acid, right? It's still true in both B and D. And then the third, what fills the third spot is acid, right? So that is option B. So option B seems to be the correct answer here. We have base, acid, acid, base. So there we go. You essentially, for the most part, you just need to identify one acid. As soon as you identify one acid, everything else, it's easy to figure out, because if you have an acid, then it's the reaction with the base, and then the conjugate acid and the conjugate base. But anyway, stories, that is 1.1. So for 1.1, the answer is B. What about 1.2? Let's go ahead and take a look at that. Which of the following species cannot act as a Bronsted-Lowry acid and cannot, right? Cannot. I was thinking can, right? Cannot act as a Bronsted-Lowry acid and as a Bronsted-Lowry base. So we are looking for a species which is not an amphilite, amphiprotic. We are looking for a species which cannot act as a base and act as an acid. We know H2O. We know fully well that H2O is an amphilite. It can act as both an acid and a base. So option B cannot be our answer because we are looking for a species which cannot. And then HSO4 minus can act as both an acid and a base. Well, let me show you how it can act as an acid. So let's say we have HSO4 minus plus H2O. This can give us SO4 2 minus plus H3O plus. As you can clearly see here, it is acting as an acid because it donates a proton. But H2SO4 plus H2O gives you HSO4 minus plus H3O plus. Clearly here we have H2SO4 as our acid and HSO4 minus as our conjugate base. So in the first reaction it is acting as an acid, and then in the second reaction it is acting as a base. So clearly this is an ampholyte. It cannot be our answer to 1.2. It acts as both an acid and a base. And we can do the same for D, right? D will also act as an acid and as a base. That is if we are really sticking to the basics. But we know that A is ethanoic acid. A is ethanoic acid. It is an acid. It doesn't act as a base. A is ethanoic acid. So the answer here in 1.2 is A, right? Whether you're getting to that answer because you know fully well that A is an ethanoic acid, or you just use this concept, you just dissolve the compound in water and see what you end up with, right? So that is 1.2. 1.3, the compound which will react with sodium hydroxide in a neutralization reaction is. So right, a neutralization reaction is a reaction between an acid and a base. So essentially what the question is asking us here is, between A, B, C and D, which one is an acid? Because if we have a base and an acid, we have a neutralization reaction. So take a look at this. We have NaOH as our base, that is sodium hydroxide, and then option A is KOH. KOH is potassium hydroxide. This is also another strong base, so we cannot have base plus base and call that neutralization. No, we need a base and an acid, so this can't be our answer. And then we have CaCO3. This is the compound you find in shells, right? And then it is basic. CaCO3 is basic. So CaCO3 and NaOH, they also can't form a neutralization reaction because they are two bases, right? So B cannot be our answer. And then C2O4 to the 2 minus. This is not a very usual compound, well, ion in this case, that we come across. So maybe this one can be a bit confusing. But if we just take a look at question 1.1, because we're not sure whether C2O4 to the 2 minus is an acid or base, right? Let's say it's not easy to see, but we can actually use 1.1 and see that C2O4 to the 2 minus is a base, as you can clearly see here. When we were identifying our conjugate acid base pair, we say that C2O4 to the 2 minus is a base. So this cannot be a neutralization reaction between a base and a base. 1.3, we have ethanoic acid. So this is our answer. The answer to question 1.3 is A. Not A, but D. It's D. It is ethanoic acid because we have a base in NaOH, and then we have an acid in CH3COOH. So clearly, this is going to be a neutralization reaction because it is a reaction between an acid and a base. Right, that is 1.3. Let's take a look at 1.4. 1.4, when sulfuric acid reacts with water, it ionizes in 2 steps, as shown in the 2 balance equations below. Well, there's a special term we use for acids that ionizes in 2 or 3 steps, right? So sulfuric acid, it says H2, so it is diprotic. It can donate 2 protons. In reaction 1, it donates the first proton, and then in reaction 2, it donates the second protons. While HCl is monoprotic because it can only donate 1 proton, right? So that is another concept that we Yeah, we brushed over when we were touching on the basics. So right, back to the question. 2 steps of which sulfuric acid ionizes. And then what is the question saying? The species are represented by letters Q and R. Okay, let's take a look. So reaction 1, we have H2SO4 plus H2O to give us H3O plus what we are referring to as Q. Well, let's put it here, what we are referring to as Q. So how can we possibly identify Q? We know that there is no element that is just going to disappear in our reaction. Everything needs to be accounted for. So take a look at this. We start with H2O. Now we have H3O plus. So clearly H2O has gained a proton. But where is the proton coming from? It's coming from H2SO4. There is no other species. That should be easy to deduce that the proton is coming from H2SO4. But when H2SO4 donates the proton, what are we going to be left with? We're going to be left with one proton, one hydrogen, right? And then SO4 minus, because we have donated one proton, and then here it is plus because it has accepted one proton. So we know that Q is HSO4 minus, right? So at this point we know that A cannot be our answer because it says Q is SO4 to the 2 minus. And then we know that, let's take a look, HSO4 minus, we know that D cannot be our answer because D says that Q is HSO4 to the 2 minus, and Q is clearly HSO4 to the minus 1, not to the 2 minus, right? So we have figured out what Q is. Let's go ahead and do the same for R. So for R, we're starting with Q. What is Q? Q is HSO4 minus. There we go. And then plus H2O. And then what is the product? The product is H3O plus R. Okay, so let's take a look. Back to the basics again. We start with H2O. Now we have H3O plus. It has accepted a proton. Where is the proton coming from? The proton is coming from HSO4 minus. So when it donates another proton, and well, let me not say another proton because now we are in a different reaction here. When it donates a proton, we're going to be left with SO4 2 minus. So this is Q and this is R. The answer to 1.4 is C, and let's do 1.5. Right. So 1.5. Let's take a look at what's happening here. Consider the incomplete chemical equation below. There we go. Looks a bit complicated, but there ain't nothing to it but to do it. Which one of the following is represented by X in the above equation? So I think here we're just following the same technique we've been trying to, well, we've been using to answer 1.4 and 1.5 and 1.1. So let's take a look. We have some X plus 2HNO3 to give us CaOH2 or OH, no, NO3, right? NO3 2 plus H2O plus CO2, right? I think this is quite easy. It is easier than it looks because we can just use brute force here. Let me show you what I'm talking about. So okay, the hydrogens, let me just change my color. So we have 2 hydrogens on the left. On the right we have 2 hydrogens. Okay, all is well there. Okay, let's do nitrogen. In nitrogen we have 2 atoms of nitrogen, right? And then in the right, that's on the left hand side, and then on the right hand side the same is true. We have N2. So there's no issues with regards to nitrogen. They are balanced. What we have on the left is what we have on the right. And then oxygen, we have 2 multiplied by O3. So this is O6 on the left. And then on the right hand side we have O3 multiplied by 2. This is O6. and then this oxygen from H2O, which will make that O7, and then on CO2 we have 2 oxygen atoms, so this will give us a total of O9. So we can see that issues are arising at this point. 6 oxygens on the left, 9 on the right. So we know that in X, some way somehow we need to have an oxygen, right? We know that for sure. We're just following the basics. What's on the left must be on the right. Okay, so that is with regards to oxygen. And then when we move to the right hand side, we have calcium on the right hand side, and then on the left hand side we have no calcium. So we know that at least we need Ca as part of X, some way somehow, right? We don't know how it will look like, but we know that we at least need calcium on the left, right? So that is Ca. And what else do we have? I think we've covered hydrogen and all is well. We need carbon. On the right hand side we have a carbon, and then on the left we don't have a carbon. So it is easy to see that we also need a carbon on the left hand side. So we have calcium, we have oxygen, and we have carbon. Okay, how many calciums do we have on the right? We have 1. How many oxygen do we have? Well, let's start with carbon. How many carbons do we have on the right? We have 1. How many do we need on the left? We need 1, obviously. And then let's come to oxygen. On the right, we have 9 oxygens, and then on the left, we have 6. The difference is 3. So here we need 3 oxygen. So on the left, in place of X, we have CaCO3. So the answer to 1.5 is D. We are using brute force here. Even if you don't have an idea of what chemistry is all about, even if you just look at the mathematical, if you just solve this problem basing it on math, we should end up with CaCO3. So the answer to 1.5 is D. Let's do question 2. So question 2, consider the following acid-base reaction. And then 2.1.1, define an acid in terms of the Lorentz-Bronsted theory. Also, the Lorentz-Bronsted theory is the easy one. So an acid is a proton donor, right? So proton donor, and then we have 2 marks. Yeah, 1 mark for 1 word. Okay, that is 2.1.1. Then 2.1.2, write down the formula of the 2 acids in the above reaction. Well, we are back to acids-base conjugate pairs. Let's go ahead and do that one more time. HCO3 minus plus NH3 to give us CO3 2 minus plus NH4 plus. Right, so we have done 2.1.1. We've already defined what an acid is according to the Lorentz-Bronsted theory. Now we need to write down the formula of 2 acids in the above reaction. Okay, so let's take a look. HCO3 minus. It doesn't really matter what you start with. You can start with anything, really. Let's start with NH3. Right, so NH3. If it is an acid, we should have NH2 minus. It has donated a proton. And then if it is a base, we should have NH4 plus. It has accepted a proton. So let's take a look. We have NH3, and then we end up with NH4 plus. So clearly NH3 accepts a proton. If it accepts a proton, it is a base. So this is a base, right? And then we are done essentially. If that is the base, this is its conjugate acid. This is gonna be a base, and then this is the conjugate acid. So the formula of 2 acids in the above reaction. Well, HCO3 minus, it donates a proton to become CO3 to the 2 minus. Which other acid do we have? We have NH4 plus. It is a conjugate acid to the base NH3. So the answer to 2.1.2, HCO3 minus and NH4 plus. right? 2.1.3, define the term ampholyte. Well, an ampholyte is a substance that can act as an acid and as a base, right? It can act as both an acid and a base. So that is 2.1.3. 2.1.4, right? Write down the formula of an ampholyte in the above reaction. Write down the formula of the ampholyte in the above reaction. So let's go ahead and take a look and see what is happening. So what is our ampholyte? Let's take a look at the reaction that we have. Let me just change my color here. I'm just giving myself some time to think here in changing the color. Right. So we have HCO3. Let's start here. We have HCO3 and NH3. Right. NH3 is a base. And then NH4 plus, it is an acid. We don't have such thing as NH2 minus. We don't have such a thing. So NH2 minus, it does not exist. This is not a thing we have in chemistry. So we know that NH3 cannot act as an acid. It cannot donate and become NH2 minus. So this is out of the way. We know that this cannot be true. And then CO3 2 minus, that is our base. Well, it cannot donate a proton to become CO3 to the 3 minus because it doesn't have a proton. So this cannot be an ampholyte, right? It is acting as a base in this case. Can it donate a proton? No, it cannot because it doesn't have a proton. And then on the other hand, acid NH4 to NH4 plus. Okay, if it is acting as a base, it needs to then become NH5 to the 2 plus, and this is technically impossible. How can you show that is technically impossible, or how can we reach to that conclusion? Try drawing a Lewis structure diagram for NH5 to the 2 plus and see what you end up with. This is technically impossible, right? So we know that NH4 plus cannot act as a base. HCO3 minus, it is an acid, but it can also act as a base. How can it act as a base? Okay, take a look at this. H2CO3 plus H2O. This can give us H3O plus HCO3 minus. No issues arise whatsoever. So you can see that this is the acid and then this is the conjugate base, right? So in this case, it is acting as a base, but in our reaction, it is acting as an acid. So it can act as both an acid and a base. So 2.1.4, the answer is HCO3 minus. It can act as both an acid and a base, clearly. And then 2.1.5, write down a balanced chemical equation to show how the ampholyte named in question 2.1.4 above reacts with water, in which water acts as an acid. Okay, let's see. HCO3 minus plus H2O. We are saying that we need water to act as an acid. So water needs to donate the proton, and HCO3 minus needs to therefore accept the proton. Okay, so we would have H2CO3 plus OH minus. Okay, let's take a look at this and see if all is well. Write down a balanced equation to show how the ampholyte named in question 2.1.5 above reacts with water, in which water acts as an acid. If water acts as an acid, it should donate a proton, and HCO3 minus should accept. When HCO3 minus accepts, it becomes H2CO3. Okay, that is well. And then if H2O donates a proton, it acts as an acid, then it will become OH minus. That is also perfectly fine. So that is the answer to 2.1.5. Okay, let's move to 2.2 and hear the stories. So in 2.2, CO3 to the 2 minus in the above reaction is reacted with 20 centimeter cube of 0.2 mole per decimeter cube of hydrochloric acid according to the following balance equation. Okay, write down a reason why Cl minus is referred to as a base. Write down a reason why Cl minus is referred to as a base. So take a look at this. We start with HCl, which is hydrochloric acid. It donates a proton, and we are left with Cl minus. Right. When we define a conjugate acid or a conjugate base, we say that it is the ion, it is the space that is left after an acid has donated a proton or after a base has accepted a proton. Okay, so Cl minus is what is left after an acid has donated a proton. It is a conjugate base, so that is why we refer to it as a base. It is what is left after an acid has donated a proton. Okay, that is 2.2.1. Then 2.2.2, calculate the number of moles of hydrochloric acid reacted. That is for 3 marks. Let's take a look and see what is happening here. So it is reacted with CO3 to the 2 minus is reacted with 20 centimeter cube of 0.2 mole per decimeter cube of hydrochloric acid. So we have the volume, we have the concentration, we are looking for the number of moles. We are really sticking to the basics here. Concentration is equals to the number of moles divided by the volume. So what is the concentration? 0.2. And then the number of moles is what we are interested in. And then the volume is 20 centimeter cube. We can just multiply it by 10 to the minus 3 and we have converted it to decimeter cube. Right. So let's cross multiply. Number of moles is equals to 0.2 multiplied by 20 times 10 to the minus 3. So 0.2 multiplied by 20 times 10 to the minus 3, 0.004 moles. So there we go. That is the answer to 2.2.2. There's something really complicated here. Let's do question 3 and see what is going on. So question 3, 2 acid-base reactions are shown in the chemical equation below. Okay, and then 3.1.1, define a base according to Arrhenius theory. Arrhenius theory is the difficult one of the two, and then base is a substance that ionizes or dissociates in water to produce hydroxide ions. Right? It is a substance that ionizes or dissociates in water to produce hydroxide ions. So that is 3.1.1. What about 3.1.2? I'm glad you asked. Write down the formula of a conjugate acid of OH minus in reaction 1. Conjugate acid of OH minus in reaction 1. So in coming to the conclusion that Cl minus is a base, well, the reason we say that Cl minus is a base, it is because it is the space that is left after an acid has donated a proton. It is therefore a conjugate base. So here, a conjugate acid of OH minus in reaction 1. Okay, so let's take a look. NH3 becomes NH4 plus. It accepts a proton. And then H2O becomes OH minus. It donates a proton. So a conjugate acid to OH minus is H2O. That OH minus is there because H2O has donated a proton. So that which donates, we know fully well that it is an acid. And then the OH minus, it's a base because it's what is left after an acid has donated a proton. So a conjugate base to OH minus in reaction 1 is H2O. That is 3.1.2, not 3.1.1. That is 3.1.2 H2O. Right. And then now 3.1.3, write down the formula of a conjugate base of HPO4 to the 2 minus in reaction 2. I don't think these questions are difficult per se. I think we are really sticking to the basics here. So let's take a look at conjugate base to HPO4 to the 2 minus. So we have HPO4 to the 2 minus reacting with H2O. H2O accepts a proton. So from H2O to H3O plus, it has clearly accepted a proton. And then HPO4 to the 2 minus donates a proton to become PO4 to the 3 minus. So what can we say about that? PO4 to 3 minus is the conjugate base of HPO4 to the 2 minus, because it is what is left after the acid has donated a proton, like we are emphasizing. So the answer to 3.1.3, PO4 to the 3 minus. And why is that so? It is what is left after an acid has donated a proton. Okay, the question that follows. Methyl orange indicator is added to the mixture in reaction 1. Right. Methyl orange indicator is added to the mixture in reaction 1 above at the completion of the reaction. The color change of methyl orange indicator in acidic and basic solutions is shown in the table below. Color in acidic solution, it is red. So if the color turns red, then that solution is acidic. And then color in basic solution is yellow. So if the color turns yellow, then we know that the solution is basic. And then 3.1.4, define the term acid base indicator. Yeah, this is not a very common definition, but an acid base indicator, it is a weak acid or a weak base which color changes as the H plus ion concentration or the OH ion concentration in the solution changes. So a weak acid or a base that will change color if the concentration of H plus changes or if the concentration of OH minus changes. Right, so that is an acid base indicator. It changes color when the concentration of H plus changes or when the concentration of OH minus changes. That is suitable. That is a good definition, because we need an acid base indicator to change color when a solution becomes acidic or if a solution becomes basic. So if it changes because the concentration of H plus has changed or because the concentration of OH minus is changed, then that is suitable because it is there for acidic or basic. You just need to know what the color change is going to be if it is acidic and what color change it is going to be when it is basic. That is 3.1.4. 3.1.5. What is the color of the indicator in the reaction mixture? Give a reason for the answer. So the indicator is added in reaction 1. So let's zoom in reaction 1 and make sense of what is happening here. So, let me just erase this. So, reaction 1. Well, we know that H2O, if you have an acid, is going to act as a base. And then if you have a base, it is going to act as an acid. So take a look at this. We start with H2O and then we end up with OH minus. So is it acting as a base or is it acting as an acid? Clearly it is acting as an acid because it has donated a proton from H2O to OH minus. So H2O is an acid, right? And then we know that NH3 is a base, right? But then even if you were not aware of that, just looking at how H2O behaves, you should reach the same conclusion that NH3 is a base. So what is the pH of H2O, right? The pH of H2O is 7. So what is deciding whether the solution is acidic or basic is NH3, because we know that the pH of H2O is 7. So if you have a base, then the pH will be greater than 7. And then if you have an acid, the pH is going to be less than 7, and then then H2O will therefore act as a base in that case. So clearly here, because H2 is acting as an acid and we have NH3 as a base, then at the end of the reaction, our mixture is going to be basic. So what is the color of the indicator in the reaction mixture? It should turn yellow here, because it is said that the color in basic solution is yellow. And we have H2O, which the pH is 7, NH3, of which the pH is greater than 7 because it is a base. So the answer to 3.1.5, we have yellow. Give a reason for the answer. Well, the reason is because the solution is going to be basic at the end, right? You can also see that by the presence of OH minus. OH minus is hydroxide ions. We know that hydroxide ions It's what you get when a base ionizes or dissociates. You get OH minus, right? Okay, and then 3.2. Let's take a look. Let's see what is happening here. 3.2. Write down a balance equation for the dissolution of ethanoic acid. Right. I'm not sure if this is the correct term where we're supposed to use dissociation, but okay. CH3COOH in water. Let's go ahead and take a look. So CH3COOH plus H2O. We know fully well that this is ethanoic acid. So because it is an acid, it should donate a proton. And then H2O must act as a base. It must accept that proton. So the products that we're going to have CH3COO minus plus H3O plus. The acid has donated the proton to become CH3COO minus, and then H2O, which is acting as a base in our case, has accepted the proton to become H3O plus. So that is ethanoic acid in water. It will produce hydronium ions. We expect an acid to produce hydronium ions when dissolved in water. That is 3.2. Question 4. Looks like things are starting to get a bit interesting here, but we are here for that. 4.1. The Bronsted-Lowry and Arrhenius theory are used to define acids and bases. We know that by now. And then 4.1.1. Define a base according to Bronsted-Lowry theory. Define a base according to Lowry-Bronsted theory. Lowry-Bronsted is the easy one. So base is a proton acceptor. Right. So that is 4.1.1. We shouldn't be getting that wrong. A base is a proton acceptor. Okay. 4.1.2. We're given a couple of reactions here, right? And then the question is saying the reaction that illustrates Arrhenius theory. Okay, between A, B, and C. So Arrhenius theory says that a substance that produces, it says that an acid will produce hydronium ions or hydrogen ions when dissolved in water, right? And then a base will produce hydroxide ions. So we are looking for that. Which equation produces hydronium ions, or which equation produces hydroxide ions? Let's take a look at equation A. In equation A, we don't have hydrogen ions, hydronium ions, or hydroxide ions. So that is not a good illustration of Arrhenius theory. Reaction B, same is true. We don't have a hydrogen ion, we don't have a hydroxide ions, we don't have a hydronium ions. Not a good illustration of the Arrhenius theory. But equation C, you can clearly see, well, not equation C, but reaction C, you can clearly see that there is hydrogen ion produced, there is H plus, when HCO4 minus ionizes. So the answer to 4.1.2 is C, because clearly an acid is producing hydrogen ions, and that is what Arrhenius theory says. It defines an acid as a substance that produces hydrogen ions when dissolved in water. Okay, 4.1.2. 4.1.3. A substance that can act as an ampholyte. A substance that can act as an ampholyte. From the reactions A, B, and C right down there, substance that can act as an ampholyte. Do we have H2O as one of the reactions here? It's one of the reactions, because if I have H2O, I'm just jumping straight to H2O and then I call it a day. Okay, I do have H2O in reaction A. Well, in reaction A, it is just acting. It's a product there in reaction A. So let's see, do we have any other equation with H2O? We don't have any other reaction with H2O. So whether it is acting as an acid or as a base in reaction 1 is not really gonna matter, because we don't have an opportunity to demonstrate that it is acting as the other in another reaction. Okay, but I'm realizing here that in reaction B we have HSO4 minus, and then in reaction C we also have HSO4 minus. Let's see if HSO4 minus acts as both an acid and a base in these reactions. So in reaction B, it accepts a proton to become H2SO4 minus. So if it accepts, then it is a base in reaction B. Okay, and then in reaction C, it donates to become SO4 minus. So it is an acid in reaction C, I meant. So it is acting as both an acid and a base. And then 4.1.3, the answer is therefore HSO4 minus, because clearly in B it is acting as a base, and then in C it is acting as an acid. Okay, and then 4.1.4, a conjugate acid base pair in reaction C. Okay, so reaction C, HSO4 minus, it's our acid. It donates it donates a proton to become it donates a proton to become SO4 to the 2 minus. And then we know that a conjugate base, it's what's left after an acid donates a proton. So the pair HSO4 minus and SO4 2 minus. So there we go. That is 4.1.4. Okay, 4.2, grade 11 learners uses 2 steps to react sodium carbonate with concentrated sulfuric acid. In step 1, they prepare 250 centimeter cube standard solution by dissolving 5.13 grams of Na2CO3 crystals in distilled water. They reacted the prepared Na2CO3 with H2SO4. Okay, right. The reaction occurs according to the following balanced equation. And then 4.2.1, define an acid according to Arrhenius theory. Right, we're getting tired of these definitions. I think we have defined an acid and a base as according to Arrhenius theories and Lorentz theories. In these questions collectively, we have defined everything, I think. So an acid is a substance that ionizes to produce hydrogen ions when dissolved in water. That is 4.2.1. So 4.2.2, calculate the concentration of Na2CO3 in the standard solution. Okay, right. Let's take a look at the information that we have, because physical sciences is just a matter of, you're given information, you have a principle, and you use the principle to find the unknown using the information that we have. So here, the concentration is our unknown. We're trying to figure out what the concentration is. And then what information do we have with regards to Na2CO3? Okay. We know that we have a mass of 5.13 grams that is dissolved in distilled water. So the mass is equals to 5.13 grams. And then the volume of the distilled water, right? Because we have some water here and we are adding Na2CO3. The volume of the water is 250 centimeter cube. Okay, so concentration is equals to number of moles divided by volume. So we have the volume, we don't have the number of moles, but we can find the number of moles using the mass, right? Number of moles is equals to the mass divided by the molar mass. Okay, so concentration is equals to, in place of number of moles, mass divided by molar, we divide everything by V. This is just equals to the mass divided by the molar mass multiplied by the volume. So we can just use this equation to find the concentration of Na2CO3. So what is the mass? The mass is 5.13. Okay, and then the molar mass is sodium is 23, so we have 23 multiplied by 2, and then carbon is 12, oxygen is 16, you multiply by 3, You multiply that by 3 and we get 106, multiplied by the volume, which will be 250 times 10 to the minus 3. We are converting it to decimeter cube by doing that. So 106 multiplied by 0.25. Right, let me see what I get there. I'm getting 0.2 moles per decimeter cube. That is the concentration of Na2CO3, 4.2.2. What about 4.2.3? We're looking for the number of moles of H2SO4 that reacted. The number of moles of H2SO4 that reacted. Okay, we're looking for the number of moles of H2SO4. We're looking for the number of moles of H2SO4. What can we use? We can use the number of moles of Na2CO3 and the balancing coefficients of the two. Because take a look at this. The number of moles of Na2CO3 is 2. The number of moles of H2SO4 should be 1:1 because of the balancing coefficient. So we just need to figure out what the number of moles of Na2CO3 is, and then we have the number of moles of H2SO4 that reacted. Take a look at this. At this point, we have the concentration of Na2CO3, and we also have the volume. So finding the number of moles should not be that difficult. So the number of moles of H2SO4, we now know that it is equals to the number of moles of Na2CO3 will be equals to the concentration of Na2CO3 multiplied by the volume of Na2CO3, right? Okay, because we have established this relationship, we are then able to do this, right? So before you establish this relationship, you can't do this. So the concentration 0.2, the volume 250 divided by 1000. So let me just put that in my calculator and see what I get. I'm getting 0.05 moles.